Hi guys, and welcome to this tutorial. I got a lot of requests that if I can give a very brief, not very long sort of tutorial for global buckling of submarine or subsea pipes, the oil and gas pipelines, for example, in under the sea. So in this tutorial, I'm going to show you how to perform buckling and post-buckling analysis using ABAQUS for this kind of pipelines. Again, I will idealize a lot of things. I will remove a lot of realistic boundary and loading conditions so that it doesn't become similar to what we do in the industry. So this is, if you are not familiar with pipelines and subsea pipelines and oil and gas pipelines, then I suggest that go back and have a look at the literature, because I will be using a lot of terms or jargons which are more normally used in pipeline design industry. So again, apologies for that, but again, idea of this thing is to give you an overview of how to perform this, and again, you can use ABAQUS to do buckling and post-buckling analysis for any structure rather than just a pipeline itself. If you work in the pipeline industry, then as you can see on this slide, DNVGL ST F110, which is a kind of a standard used in subsea oil and gas industry, for example, and it is specifically written for global buckling of submarine or subsea pipelines. I will be using that. You can use that as well. It basically has a guideline to assess the buckling or instability of your pipeline based on analytical methods which are derived from experiments in majority of the cases. So you can look into that, and at some point you can be asked to do a detailed FE analysis as well, so in the code itself. So I'm going to do the FE analysis, and I'm not going to comment on the technicality of the analytical relationships. There are many courses which I take on pipelines, so I deliver on pipeline design, so maybe in future I will come back with that. So for the material properties, again, every standard asks you to define in a different way based on their own analogy. In this case, I'm going to define the true stress strain response of steel. Again, I'm using, I think, S255 grade steel, and again, it's an assumed value. It may not be the correct value, correct steel used in pipeline in majority of the cases. So in any case, so I'm going to define those stress strain curves based on DNVGL RP C208, which is compliant to EN 10025 and an EN 10225. Again, they all ask you to define the plastic part of the stress strain curve if you are allowing or using a nonlinear finite element methods. I'm assuming my pipeline, again, it's an idealized case. All similarities will be coincidental. So my pipeline length is 10 meters. Generally, pipeline lengths are in kilometers, thousands of kilometers in some cases. So this is a very short length to do a buckling analysis, in my opinion. My outer diameter of the pipeline is assumed to be 400.2 millimeters, which is coming from the nominal diameter. So that's why you have these decimals there. And the wall thickness I'm assuming to be 16 millimeters. I'm assuming my pipeline to be only single steel pipeline. This means there is no coating, no concrete coatings, insulations, etc. in this case. The internal pressure of my pipeline, I am assuming it to be 8 megapascals, while the external pressure is 4 megapascals because it's under sea, so you have high pressure. So depending on the depth, your external pressure varies. So again, you can see it's an internal overpressure pipeline because your internal pressure is higher than the external pressure. I am also assuming the effective axial force, which is an important driving force in the pipeline stability or deformation. So that is the force which is acting along the axial direction of the pipeline. It is generally incompressive. It's compressive in nature, and in this case I'm using this arbitrary value. Again, there is no functionality to that. This axial force, if you look at the derivation and theory behind it, it is dependent on the temperatures, pressures, and other operating conditions and gap effects, etc. While in this case, what I'm assuming is I have got this value from all these operating parameters except for the internal and external pressures, and that's why I'm going to apply internal and external pressures to the pipeline directly in my FE model. If I have computed that, I can apply that as well. Another important thing is I'm giving you a single value here. In general, this force is computed in newtons per meter or per unit length. So depending on the data at each corresponding KP, you basically have to compute that, and then you have to apply as a boundary condition throughout the length because it varies as you move along the pipe. For buckling analysis, if it's a straight pipe, the load will be very high because you will have to do a lot of compression until unless you have some kind of imperfection or out of straightness or bending, and then that will cause kind of buckling. So in this case I am already creating an imperfection or curvature in the pipe. So I start with a straight pipe, and then I say there is an external force, which could be a trawl or something else which is pulling the pipe. So it will pull the pipe and it will create some kind of curvature or imperfection in the pipe, and then you can easily see buckling in the pipeline. So that's what I'm doing here. So there are two mechanisms, as I said. One is this, and the other one is if you are laying your pipeline on the seabed, so your seabed is rough, it has a very rough profile, so you can have crusts and troughs on your surface seabed. So again, in that case you can have this kind of imperfection, and that can also be more prone to upheaval buckling or other types of buckling, lateral buckling as well in some cases. So for this trawling case, I can have a force which is acting onto it in an easy way. What I'm doing is I'm applying a gravity force, and I say this gravity force will cause this pipe to bend in this direction depending on the weight density of this pipe, which is the density of the steel plus whatever it is inside. In this case I'm assuming it to be most of the weight is coming from the pipe itself. So I apply this gravity in the opposite direction so that I get this kind of curvature. Again, you see I have made this unrealistic boundary condition to do that, but in reality you can do the same, and you can apply it in the downward direction as a gravity, and then you can see what happens to your structure then. Also, I am assuming the one end of the pipe in this case will be fixed, because I assume that, as you know, as I told you, my frictional force is dependent on the soil pipe interaction. So I know that value, and I know my effective longitudinal force, again depending on pressures and temperature, will change as I move along the pipe. So at some point in time I will find out that my force, compressive axial force, is equal to the frictional force per unit length, and at that point cannot be moved or slide on the soil then, and that's called the anchor point. So I am assuming one end of my pipe, in this case out of this 10 meters, to be an anchor point. So I will fix that point in all directions so it cannot move due to this condition of constraint. Again, this is, you need to know that from your calculations or your pipeline case. It varies from case to case where it is reality. Okay, so let's start with the tutorial. Just a quick demonstration. I'm not going to make a whole model as people have requested. I have made and run the simulations, and I will show you how I have done it in a quick time. And I hope that you already have gone through my other lectures and tutorials, so you know, or you're familiar with the ABAQUS environment and how to create geometries and define material properties, etc. So let's go with that. So initially what I will do, I will start with this pipeline. So what I did was I created a extruded shell structure. I created this circle, and then I extruded along this direction. It could be in positive or negative depending on that. So that's what I'm trying to show you here. So you see, this is the sketch I'm trying to speak about, and then I have extruded that using the extrude command. And for the extrusion I have used 10 meters. As I told you, my pipeline I am assuming to be 10 millimeters. So again, I'm using millimeters here, so you have to be careful that all the units have to be consistent with the millimeters. Then I go to the property module, and then I define the material properties. In this case, for the linear buckling analysis, I can live with the elastic properties, so I need to define the steel density and also the elastic properties. So in this case I don't need any standards or anything to define the properties, because I don't need that, but later on I will be using plastic properties. Once I have defined the material properties, I need to assign it to the pipeline. So I will create a section as I did for the in my previous tutorials, and I will define a thickness because it's a shell section, and I am defining the pipeline wall thickness to be 16 millimeters as given in the previous slide. And then I just assign it to the pipeline, and it has section 1 which has material 1 property. It's a shell section, and I'm defining it as a midpoint. Once I have done that, then I have to assemble the part. So I go to the assembly module, and I bring everything here. In this case it was just one single pipe. Then I go to the step module, and I define a buckling step, which is basically based on the fact that you can create it by selecting the linear perturbation step here, and then you can click on the buckle, and then it will open that window, this window here. So I'm using subspace here, and then I'm asking for 10 eigen modes as you see here, and then I am also using 300 iterations here to be on the safe side. Rest is just default. For the interaction, since there is no interaction, what I'm going to do, I will apply all the boundary conditions at this surface. As you see, I have zoomed it here, and so for that I have created a reference point at this surface, at the center of that point, and you can create this reference point like this using this command. And then I constrain this reference point by using coupling, kinematic coupling, and that kinematic coupling will mean that whatever I do with this reference point will do the same for the whole periphery of this whole thing. And that's why you see this line, because this is now constrained with the whole surface. So whatever you do here, the whole surface behaves the same. There is no contact conditions here because we are not expecting or looking for any contacts, and we will stop our simulation before it makes any contact with other shapes. Then I go to the loading and boundary condition. The first load I'm applying is a concentrated force. Again, this is an effective longitudinal force which is in compressive direction, as you can see here, and this is in the Z direction. So I apply that based on the data given to me in the previous slide. And so that's what I've done here. The other things I have to define are the internal and external pressures. So this is my external pressure based on the depth of the pipe, which is rho times g times h. So if I know the density of water, acceleration due to gravity, and the height or depth, then I can find out what sort of pressure my pipeline is under. And this is my internal pressure depending on the operating conditions of the pipeline. Again, you can remove that if you already have incorporated those in the other effective longitudinal force. And this is the what imperfection type I'm applying. So I'm applying a negative sort of condition, which will be more like a gravity, but you can apply a force at the center or something else like a disturbance in that direction to cause some kind of bending in your pipeline or buckling in your pipeline. On this side, I have fixed the whole edge. As I told you, this is basically based on the fact that I'm assuming the other end to be anchor point in my pipeline. And for this point also, I'm not allowing it to move in any other direction than the longitudinal direction or axial direction. So I'm fixing all the other things. Again, in reality, if you have the data that your pipeline can move around in lateral or other directions, then you can prescribe those as boundary conditions as well, if there is any data available. So I'm going for the extreme conditions right now. I have created a shell mesh, which is S4R mesh. Again, you can decide what mesh you want to do, and then I go to the job module and I run the analysis. So once I have run the analysis, I can look at the base state, which is very much the same as the initial state, and then I move to the next one, which is basically my mode 1, and in this case I get an eigenvalue for that. And what you see here is the walls near the support are very much gonna have a large displacements, most probably, of forces. So these other regions might have a lot of issues during the analysis or buckling. So let's see if we can capture this kind of thing, but at least we have got the values. Again, you see here some negative values, and these negative values or some eigen modes will mean that if my loading condition get opposite, like for example internal pressure is lower than the external pressure or force direction changes, then my eigen mode can be in the opposite direction. So this could happen in that case as well. So I'm going to go for the first mode in this case. So what I will do now, I will copy the model and I will call it model 2 because I already have everything there. But what you see now is I have the model 2 with everything with the previous model. I need to change something, but before doing that and before running model 1, I need to do something which I forgot to mention. So what you have to do is you have to write a note file before you submit. So you have to select edit keywords, and then at the end you have to write note file. As you see here, some people use note fill as well, and write U so that you get displacements as an output, which you will then be using for your nonlinear buckling analysis. So that's what I have done. Then I run it, and then obviously I have a fill file saved in the same folder as this one with the same name as model 1 job. And then I copy the model, and now I will start to modify my model 2. So now I'm in my model 2, and I will start to look at everything from scratch. That is starting from part. It remains the same. I don't change anything there. For material properties, definitely I need to change the material properties because I need now plasticity in the model. So again, for plasticity, I told you I'm using in the DNV and EN standards for defining the true stress strain curve for plastic part of the curve. So you see here I have an additional card which is the plastic part, and that's basically based on those standards. In this case, you can also use other standards as well if you want. So I just try to mix few things up so that it's not very much similar to some specific problem. Then I go to assembly, again the same process, then go to the step, and now I can do what I can do. I need to replace my step with a RIX step. So how I do it is I can create it from here. I can remove the previous one and I can create a new one here, or I can just click, I go here on this side, open this thing, and I right click and I can say replace the previous step with the RIX step. So this is my static RIX step, and I have general geom on in this case, which is arc-lambda. Once I have done that, I don't need any interactions, no context as usual. The coupling remains the same for the reference point with the surface. All the loading and boundary conditions will remain the same except for the effective longitudinal force, because I'm going to use now the value of the eigenvector for mode 1, which is this one in this case. The rest of the material property, the rest of the boundary condition I don't touch. I don't do anything with that, because effective longitudinal force is the one which is the most critical parameter in every case and which can be varying throughout. So that is done. Boundary condition, lateral direction, and also fully encasted or fixed on the other end. Anchor point, mesh is the same, and then I run the job. But before running the job, what I have to do is I have to go here and I have to edit few keywords, because now I have to define an imperfection manually based on my previous analysis using my linear buckling analysis. So what I will do, I will go and just above the step definition, I will define an imperfection keyword. I will say step number, take the data from step 1, and the file name, which is the name of this file, as you see here, buckling underscore pipe. I'm using mode 1 and I'm saying only apply 10% of that imperfection values. Again, this 0.1 is a very controversial thing, and you need to do a lot of convergence study in the industry that to see which kind of imperfection and what percentage will give you the right answer. And again, this is another point of discussion. So once I do that, I rerun it, and once it's finished or whatever, then I just go to the results and I start looking at the results, and you see these are the areas which are under a lot of stress and strain, and they have already distorted, and you see how it looks like at the center due to the buckling. Buckling itself is not a failure mode, remember, it's an instability which can cause different types of failure. In this case, you can see your failure is somewhere here. Your walls are already having a lot of strain in tension and compression direction, and they're bulging out, and also you have ovalization of your pipe first, and then it becomes like this, and after some time it will completely be squished. So in a quick way, I have tried to show you that, and you can see you can generate some nice animations of stresses, strains, and everything. And again, you may try different things based on this. You can also see how much load, after how much load you apply, will it fail. So you can plot the load proportionality function. So let's see if we can go to that. Yeah, so you go to the XY data manager, create history output, and then you will look for LPF value or LFP value. So if you go down there, so it's load proportionality factor, as you see here, and you can see this is how the whole response looks like. You are failing above 12-20% of the load in this case, and this is a snap through sort of process, and it's going towards its direction, as you see here. So it goes up and then it goes down after that instability behavior. So I hope this short tutorial or demonstration makes sense and you are able to perform similar analysis. Again, the correctness of these boundary condition assumptions might be questionable because I try to assume a lot of things, but I hope this gives you an idea about the whole process of doing that. So again, as an FEA analyst, you need to decide what sort of boundary conditions you're going to use for your real structures at the end of the day. So thank you very much for watching, and I hope to see you in the next video or tutorial. Bye.